Hey, here we go, guys. Today we're going to talk about naming compounds again. I've already given you a couple of videos, just kind of overview of naming compounds and then getting into naming molecular compounds. But today we want to get into the ionic, the first of 3 different videos we'll do on ionic compounds. So these will just be your basic ionic compounds, okay? So let's jump into it here, see if we can't make this thing work for us. When it comes to ionic compounds, one of the things that I think that people get confused on once we start bringing all these different types of compounds together is how do I tell the difference between one type of compound and another, right? So molecular compounds, really easy to tell them apart because they're nothing but nonmetals. There's no metals in there. It's just 2 nonmetals bonded together. With ionic compounds, we're going to have a metal and a nonmetal, right? So if you have a metal and a nonmetal, then you've got an ionic compound. Now, could be a little bit more tricky because there's polyatomics that's sometimes involved in ionic compounds. So the most polyatomics that we learn are negatively charged. They'll be taking the place of a nonmetal, but there are a few positively charged compounds, ionic compound, excuse me, I can't talk, polyatomic ions that could take the place of the metal. All right, so it's possible that the metal or the nonmetal not be there and there be a polyatomic instead, but it's still something positively charged and something negatively charged. Typically speaking, a metal and a nonmetal. Okay, so if I see a metal, then I know it's an ionic compound. If I see a polyatomic and there's not a hydrogen in front of the polyatomic, in other words, you have a metal and a polyatomic, it's not hydrogen and then some polyatomic, then it's definitely an ionic compound. If you see parentheses, the only types of compounds where we're going to be looking at that has parentheses is if it has a parentheses, then it's an ionic compound. Molecular compounds won't have them. Acids won't have them either. Okay, so if you see parentheses, then that means that for us right now that we're dealing with ionic compounds. All right. No prefixes. If you look at the name and there's no prefixes in the name and it's a binary compound, in other words, there's just 2 parts, there's just 2 elements, then it's definitely an ionic compound, okay? And then if you see stock system, so when you look at the name, if there's in between the 2 words, between the 2 names, there's a parentheses and there's some Roman numerals there, that means the stock system, that's definitely an ionic compound. So those are just some keys to recognizing if it's an ionic compound, okay? Getting into naming it, naming ionic compounds is actually really easy, okay? All we do is we just name the first element, which is going to be the metal, okay? And then we will name the second element, which is going to be the nonmetal, but instead of whatever ending that element has, we're going to change the ending to ide, I-D-E, just like we did with molecular compounds, okay? So there's no prefixes here. It's just name of the first element, name of the second element with the "ide" on the end. Easy peasy, lemon squeezy, right? So a couple examples of this. If we have NaCl, Na is sodium, Cl is chlorine, but we change the ending chlorine to chloride. So it's sodium chloride. Here we have Li2O. The Li is lithium, so we would call this lithium. And the O is oxygen, but we changed the ending to ide once again. So it's lithium oxide. And then down here, we have Ca3N2. Right? Ca is a metal. So, hey, that means that it's an ionic compound because there's a metal there. So what is that? That's calcium. And then the N is nitrogen, but we changed the end of nitrogen to ide. So it's calcium nitride. Now, notice here, there's no subscripts here at all. Here, there's a subscript on the first one. Here, there's a subscript on both of them. But those numbers were not at all part, those subscripts were not at all part of the naming process, okay? So, doesn't matter. Numbers don't matter for the naming process. We just name the first, we name the second, we put an ide on the end if it's an ionic compound. With molecular compounds, remember, we use the numbers to write the prefixes, right? But there's sodium chloride only goes together one way with 1 sodium and 1 chloride, so we don't have to say how many of them it is because it always works that same way, okay? Molecular compounds, we use those prefixes because a lot of times two elements can go together in multiple ways. So you can have a carbon monoxide or a carbon dioxide. So we have to differentiate between the two with the prefixes. Okay. So no prefixes here at all. Numbers aren't part. The numbers do tell us how many do we have of each. So we have one of each. Here we have 2 and 1. So for a total of 3 atoms, but it's not involved in the name. All right, that's pretty easy. When it comes to writing the formula is not any harder, but it looks like there's a lot more steps to it. Okay, but it's not bad. Trust me. Okay, so when we write the first thing we do, we have the name, right? We will write the symbol for the metal, the first element, including its charge, its oxidation number, and then we will write the symbol for the nonmetal, which is the second element, including its charge. And then what we're going to do is we're going to take and we're going to swap and drop. In other words, we're going to swap the numbers with what elements they are, and we're going to drop them down to their instead of being superscripts, they're going to be subscripts. All right. So the goal of all this is to end up with a balanced or a neutral compound. All compounds themselves are neutral, right? So what we have to do is we have to look at, okay, what's the charge of the metal and what's the charge of the nonmetal? So how many do I need of each of these so that when I put it together, I end up with a neutral? Or in other words, when I add all their charges up, the charges add to 0. Okay? That just kind of gives an example of that. Okay? So oxidation numbers. Remember, an oxidation number is basically just the charge of the atom when it becomes the ion that it wants to become. So, group 1, they want to lose 1 electron, and so they become a +1 ion, right? Well, group 2, they have 2 valence electrons. So group 2 would like to lose both of those so they can feel like a noble gas, right? And have that outer shell completely filled. So group 2 tends to become +2 ions, right? And so on. So the oxidation number is just when that atom becomes an ion in whatever its charge is in the compound, right? That is the oxidation number. So a lot of times you'll hear me say charge instead of oxidation number. I kind of use those interchangeably because they pretty much are interchangeable. Okay, most metals can have multiple oxidation numbers. Okay, but there's a few that only has one oxidation number. So group 1 is all of group 1 is +1s. They all have oxidation of +1. Silver always has an oxidation of +1. Group 2 always has an oxidation of +2. Zinc also has an oxidation of +2. And then aluminum has an oxidation of +3. So these here, we can pretty much just kind of memorize and know those, and it allows us to work with those elements much quicker. We don't really have to look at the periodic table unless we just have to look to see, is it in group 1 or group 2 if we can't remember, that kind of thing. But beyond that, we can kind of automatically know its oxidation numbers. We'll get into those other ones that have different oxidation numbers, that can have multiple oxidation numbers. We'll do that in a separate video. That's the one with the transition metals. That's how we have to treat them a little bit different because they can have multiple oxidation numbers. They can have multiple charges. Okay, nonmetals can also have multiple oxidation numbers, but for what we're doing, working with them in ionic compounds right now, the nonmetal can only have one oxidation number in an ionic compound. So it makes things a lot easier, right? So we find out what the oxidation number is for that nonmetal by knowing how many valence electrons it has. So oxygen is, if you got your periodic table out, and if not, you might want to pause it and get your periodic table out so you can be looking at it while we're talking about this. Oxygen's in group 16. That means it has 6 valence electrons, right? So it's 2 away from having a complete shell. So oxygen wants to gain those 2 electrons, right? In the form of ionic bonding, then it wants to gain 2 electrons. In the form of covalent, remember, that's where it would be with the Lewis structure stuff that we did. That's where it would be bonding. It would be adding 2 bonds, right? It would be sharing electrons with two other atoms, right? So the oxygen's oxidation number would then be 2- or -2, right? Because it wants to get 2 more electrons, all right? Phosphorus has 5 valence electrons, so it needs 3 more, so its oxidation number would be -3. Fluorine, on the other hand, has 7 valence electrons. 8 minus the 7, remember everybody wants 8, tells us that its oxidation would be -1. So in other words, when these guys become an ion, an anion technically, a negative ion, that's the charge that they would have, okay? So the nonmetals we can just kind of know based on where they are in the periodic table. Some of the metals we can know based on where they are in the periodic table, and then others we can we have to kind of do a little bit of work there. Okay. So when it comes to doing this, writing the formula. If I take this example here, I've got magnesium nitride, right? So magnesium I know is a +2 because it's in group 2. Okay. You look on your periodic table, in group 2 you find magnesium, it's the second one down, right? Nitrogen is a -3 because of where it is on the periodic table, okay? It has 5 valence electrons, so if it becomes the ion it wants to become, it's going to add 3 more electrons, making it a -3 ion, okay? So this is the oxidation, so we wrote each of these with their oxidation. So then we rewrite the symbols, Mg and N, and we swap and drop. So the -3 tells me that I got 3 magnesium, and the +2 tells me I have 2 nitrogens. All right, so we swap and drop. Let's get out the little arrows. Ionic compounds, we swap and drop. With ionic compounds, we swap and drop. Ionic compounds, we swap and we drop. We take the oxidations and we swap and drop them. So I end up with the formula Mg3N2, which tells me I have 3 magnesiums and I have 2 nitrogens. Okay, that's making the charge here to be balanced. Okay, because the magnesiums, each of them are +2. So if I have 3 of them, 3 times 2, that gives me a charge of +6. Well, each of the nitrogens is a -3. So 2 times the -3 gives me a -6. So the +6 and the -6 balance each other out. It adds to 0. So I have a neutral compound, which is what we have to end up with, is a neutral compound. Okay. Notice that though they have signs on them, they're a plus and a minus here, they're not down here. So the superscripts are telling us the charge. They have signs. But after we swap and drop, there's no signs there, because these subscripts are just telling us how many we have of each atom in the element, okay? In general, metals lose, right? They become cations, and the nonmetals gain. That's just kind of pointing you back to why that's a plus and why that's a minus, okay? Look at another example. We have potassium sulfide. Potassium's in group 1, so that means it's going to be a +1. Your sulfur is right below oxygen in group 16, so it's going to be a -2. And then we simply swap and drop them, and we get K2S for our formula, K2S. Now, notice that the S doesn't have a 1 there, all right? Because that 1 is understood. We don't have to put a 1. We understand that there's a 1 if there's no number there, all right? So what we end up with is we end up with 2 potassiums. We end up with 1 sulfide, okay? This over here, it's just for your reading pleasure. It just kind of talks about what we talked about them ending up being neutral. We have 2 of these, each of them's a +1, right? So +1 times 2 gives me a charge of 2. And then we have 1 of these guys, but its charge is a -1. That leaves me with a -2. So 2 and the -2 add to 0. So we end up with a balanced or neutral atom, okay? A couple more examples here. With these examples, it's the exact same thing. The only thing I'm pointing out to you is this fact right here. When we get finished, if we can reduce the subscripts to a smaller or to a lower ratio, we do that with these ionic compounds, okay? So calcium is a +2, it's in group 2. Oxygen is a -2 because it's in group 16, it's got 6 valence electrons, blah, blah, blah. These are the ions that these things are going to become, the charges that they will have. So when I swap and drop, I end up with Ca2O2, all right? But since both of these numbers are divisible by the same number, they're obviously both divisible by 2, I do that. I simplify that ratio. So I divide both of them by 2, and I just end up with a 1-to-1 ratio. So I got 1 calcium, and I have 1 oxygen. So it ends up just being CaO, okay? Same thing for this beryllium carbide over here. Beryllium's a +2 because it's in group 2. Carbon is a 4 minus, a -4 because it's in group 14, right? It's got 4 valence electrons, it wants 4 more, okay? So when we swap and drop, we end up with Be4C2, but of course 4 and 2 are both divisible by 2, so I do that, right? So I take the 4, divide it by 2, and I get 2, and I take the 2 and divide it by 2, and I get 1. So we've reduced that to a 2-to-1 ratio. Instead of a 4-to-2 ratio, it's a 2-to-1 ratio, which it's still balanced, it's still neutral right here, right? So we end up with Be2C for this particular one, okay? I think that's the last of those, but I've got one more little thing for you here. I've grabbed some Legos, right? And I have put elements on here to let you see kind of what it is. I hope you can read that from there. And this is just kind of to help us with these ionic compounds to understand kind of the parts and how things go together, right? So if I take, just to show you, sodium's +1, so it's one little piece. Magnesiums are +2, so I have these, 2. Aluminum is +3 charge, so I have a piece of Lego that has 3 little humps, right? There's that. All right, so give you an example. If I have a sodium chloride, if I'm trying to make NaCl, right? Then this guy's got a +1 charge, chlorine has a -1 charge, so we can actually see that, hey, to make this compound, all we need is just one of each of these. So NaCl, sodium chloride, is just that. It's one of these and one of these, okay? So if we take another example, if we look at, I forgot what I picked up. Potassium fluoride, okay? So if I'm writing the formula for potassium fluoride, and I see that the potassium is a +1, right? And fluorine is a -1. So when I put them together, I just need one of each in order to make my compound. It's a 1-to-1 ratio. So you end up with, potassium 1+, fluorine 1-, and when you swap and drop, you just end up with KF. There's a 1 here and a 1 here. It's understood, yada, yada. Okay? So let's look at some examples where it's not just a simple 1-to-1 ratio. If we take silver oxide. Let's take silver oxide. So silver is a +1, but oxygen is a -2, right? So if I put these guys together here, then obviously this doesn't work. These guys aren't happy. There's an empty hole here. This oxygen is needing enough silver, another silver, in order to make it happy, okay? So in this case, I would need 2 silvers to go with the 1 oxygen. Oops. So this is just 1 oxygen, but these are 2 separate silver ions, right? So 2 silvers go with 1 oxygen in order to make this compound, right? So you end up with silver 2 oxide. If we go and do what we did here, then it's the same thing as far as this being a +1, the oxygen being -2, right? So when you swap, you get 2 on the silver, and you get just 1 on the oxygen, okay? So this is just hopefully to kind of give you a visual to help you to understand what we're doing here with the whole swap and drop thing, okay? At the end of the day, you're just going to do the swap and drop because it's going to be so much faster. It's not like you're going to, but you could kind of draw this out if you wanted to and say, okay, I've got silver, it's a +1, and oxygen is a -2, right? So you got your 2. So how many of these do I need to go with one of these? Because this is a set together, right? So I mean, that tells me I need 2 of those. So you could do stuff like that to help you, but the truth is, you're not going to need to do that. Okay. Next one. Let's look at zinc sulfide. Okay. So zinc, if you look on your periodic table, or if you look back here, zinc we said is always a +2. So here's my zinc, right? And then sulfide, if we look and we find sulfur, which sulfur ions is sulfide, we've changed the ending, so it's a monoatomic ion, okay? It's just, so it's an ion made from one atom, right? So we've changed that ending to "ide," but sulfide is also a plus or -2, excuse me. So zinc and sulfide just go together in a 1-to-1 ratio. I just need one of each of these in order to work. Because each of them has a +2 and a -2 charge, you just end up with your zinc sulfide. Once again, it's one of those where if we write it out, you've got +2 and -2. So when you swap and drop, you end up with a 2 and a 2. And since both of these guys are divisible by 2, I can reduce that. I can divide them both by 2 and just end up with zinc sulfide. Okay, a 1-to-1 ratio. Excellent. Let's see. Let's go aluminum chloride. I'll just do a few more of these. I think you got the hang of it. Trying to make this video short. On the other hand, it took me quite a bit of time to get all these things taped on here, so I'm trying to take advantage of what I got here. What did I say? Aluminum chloride. Forgot the L. Aluminum chloride. So aluminum is a +3 ion. So I need, if I'm working with a chlorine is just a 1-, so I'm not going to need 1, 2, but 3 of these in order to make this compound work, right? So 1 aluminum goes with 3 separate chlorines. 1, 2, 3, right? So my formula here for aluminum chloride would be 1 aluminum, 3 chlorines, right? Once again, you do the same thing through the swap and drop. All right, let's go one more. Let's say magnesium nitride. Okay, so magnesium we know to be a +2, okay, and nitride we know to be a -3, right? So if we try to put just one of each of those together, we see that we're not happy here. If I try to add another magnesium, then we're still not happy, right? So then I can add another nitrogen and see that we're still not happy. So then if we go back and we add one more magnesium, then we end up with something that works so that both parties, the nitrides and the magnesium, are happy. So what did I do? I ended up using 2 of the nitrides and 3 of the magnesiums, right? So I have Mg3 N2. Mg3 N2. And once again, magnesium was a +2, nitrogen was a 3-. So when we swap and we drop, the 3 tells me that ends up with 3 magnesium. The 2 charge on the magnesium tells me that ends up with 2 nitrogen. So Mg3 N2. Swap and drop with ionic compounds. Okay? Excellent. See you in the next video.